Hello, in this video, we present our paper, Improving Object Detection by Label Assignment Distillation. The problem we want to address in the paper is called label assignment for object detection and what it is. So in object detection, an image is divided into many small sample regions with different scales and being overlapped, which we call anchors. So label assignment aims to define the areas that contain the objects with positives or foregrounds, otherwise called negative and backgrounds. However, unlike image classification, where a category can be easily set to an image, defined labels in object detection are ambiguous due to the bounding box overlapping. For example, in this image, which bounding box should be the positives?
The classical methods assign the anchors based on the IOU, for example, if it IOU greater than 0.5. However, one problem is that anchors with the same IOU can have very different semantic meanings. Therefore, it's not correct. Therefore, in recent assignment methods such as BAA or auto-assign, we assign the anchors based on the combination of the classification and the localization performance of the anchors. Take the BAA anchor examples. At first, we select a subset of the samples and assume that they are positive. Then we compute the cost based on the performance of the current networks. Then we use a statistic criterion to select the threshold, and then the anchors with the lower cost than the threshold are assigned the positive, while the rest are set back to the negative. In this work, we present a new label assignment method that we call label assignment distillation, or in short, LADY. We borrow a teacher network to evaluate the cost instead of using the target network itself. Intuitively, because the teacher network is well trained, it can perform the cost evaluation more accurate and consistent. Therefore, the label assigned to the target network is more accurate, and we can train it convert faster. So the key advantage of LAD is that it's very simple but effective, and it's applicable to many label assignment methods. It can complement other distillation techniques as we show later, and more important, using LAD, a small teacher can improve the student network significantly and possibly surpass the teacher by a large margin. In comparison with the conventional distillation methods, such as sub-level distillations, the output of teacher network usually yield the training target and distill directly to the student. In contrast, our label distillation methods, the output of teachers are filled with the ground truth through the label assignment before indirectly distilled to the student. In Table 2, we show that our method can improve the baseline by 1.2 MAPs, and when we combine with the sub-label distillation method using Kullback label loss, we can improve by 2 MAP on the challenging COCO dataset. In the second experiment, we use a smaller teacher, which is RedNet 50, to train a larger network student, which is RedNet 101. Note that using the sub-label distillation, the performance is worse than the baselines. However, using our LAD methods, we still be able to improve the baseline by 0.7 MAP and almost approaching the baseline training with 2x schedules. When compared with the conventional label assignment methods, we can think of label assignment methods such as BAA or auto-assign actually is a special case of label assignment distillation, where the teacher network is the network itself, or we call it self-distillation. Motivated specific observation resemble both a new method called co-learning label assignment distillation, or in short, CoLAD. So in CoLAD, we train two networks concurrently. However, the role of the teacher and student network are dynamically switched based on a switching criteria. So the CoLAD can be useful when a pre-trained teacher network is not available, or even when the teacher network is smaller than the student, or when we train several models, for example. So in Table 5, we show that network trained with CoLAD outperform the baseline trained independently, or even a network that is trained for 1x schedules after joining CoLAD for another 1x outperform the one that trained for independent for 2x. Finally, in Table 7, we show that our CoLAD methods outperforms other label assignment methods. And in Table 9, we show that our methods also outperform other distillation methods for object detection. And that concludes our paper. Thank you for your attention.